Hello, in this video we put to use our knowledge of combinations to solve word problems using probability. Let's get started. So recall that we use combinations whenever we're finding the probability of selecting subgroups from different categories where order is not important. If order was important, what would we be using? Starts with a P, permutations, that's right. So we use combinations when order doesn't matter. So today we're going to put to use that idea of using a combination to figure out how many ways could I select this subgroup of items where order doesn't matter with the idea of probability. So we begin by reminding ourselves again that probability was a simple fraction, where in the numerator we had the number of ways which the desired outcome could occur, right? And in the denominator we had the total number of possible outcomes. So if you're talking about cards and you really need to get a 2, you would say, how many ways could I get a 2? That would be your numerator. And how many ways could I select a card, period? That would be your denominator. But today we're going to do things a little more complicatedly, because instead of taking just one card, we're taking a subgroup of cards, a hand of cards, which is why combinations come up. So we remind ourselves of the combination formula. If you forget how to enter this in your calculator, go back to the last video and watch one of those tutorial videos on how to use the combination formula, how to use the combination button instead of having to do the calculations by hand. Okay, so let's head into our next slide and practice probability with combinations. In example 1, it says, find the probability of being dealt a 5-card hand from a standard 52-card deck, and again here I've shown you that deck in case you've forgotten what's in there, consisting of 3 kings and 2 5s. Now this apparently in poker is known as a full house. Now I'm not testing your poker skills, so I'll always tell you exactly what kind of cards I'd like for you to find, okay? So we would like for you to find the probability of selecting a special card hand where you have 3 kings and 2 5s. Okay, so probability, as soon as you're talking about the probability, you should be thinking of a fraction, right? So we're trying to find this probability. And to do that, we need to form a fraction. So what do we put on top? Well, the number of ways that we could select the desired outcome, right? The desired outcome is from the kings, I would like to select 3. So how many ways could I select 3 kings out of my total number of kings? Well, let's look at our deck again. For each of our suits, we have 1 king, right? A king of hearts, a red king of hearts, a red king of diamonds, a black king of spades, and a black king of clubs. So there are 4 kings in the deck. In other words, 4 combination 3 is the number of ways to choose 3 kings from 4. If you go back to your previous video, you'll see how we determined that when order doesn't matter, you could use this combination formula or your calculator button to calculate this. And when we did this, I'll do it one time with the formula in case you like the formula better. We had 4 factorial, that's our n factorial. Then we had n minus r, 4 minus 3, would be 1 factorial. And we also had r factorial, 3 factorial. So in this case, you'll have 4 times 3 times 2 times 1 in the numerator, and 3 times 2 times 1 in the denominator. In other words, the 3 times 2 times 1, which is 6, will cancel, and you'll just have 4, okay? So there are 4 ways. Well, we kind of already knew that, right? That there would be 4 ways to do this, because you're choosing 3 out of the 4, and you can see by a process of elimination that there's just the 4 ways to do this. So we end up getting, for this first part, a 4 for the number of ways we can select 3 kings from the 4. So that's where we got that number here from. But we're not just selecting the 3 kings. We're also trying to select 2 5s. Okay, so 5s, they work the same way as kings in the sense of how many cards there are in the deck, right? When we look at 5s, we have the 5 here, the 5 here, the 5 here, the 5 here. There is a 5 in each of the 4 suits, so there are 4 5s in the deck. So the same thing would apply, but instead of 4 combination 3, what would we need? 2, very good. And so this, again, with the formula would be 4 factorial. 4 minus 2 is 2 factorial, and then your r is just 2, so 2 factorial again. So you would have 4 times 3 times 2 times 1 for your numerator, and 2 times 1 times 2 times 1 for your denominator. When you simplify that out, or just use your calculator button for that particular part of the problem, you should end up getting the answer of 6, okay? So there should be 6 ways to do this. So that would be the number of ways that you could select your 2 5s from 4 that are in the deck. So 6 ways to do this. So what we've done is we found out that for the numerator, we'll have 4 ways that we can select those kings, and we'll have 6 ways that we could select those 5s. Since we're doing both of them, and or both means multiply. So we'll have 24 ways that we can make that selection of 5 cards. But how many ways could we have selected 5 cards in general? Because that's how we get probability, right? Number of favorable over total number possible. Well, we did it in our last video, if you remember. Feel free to go back. But the idea there was to get the total number of possible 5-card hands in poker was to say there's 52 cards in the deck, and you're choosing, where order doesn't matter, you're choosing 5 cards. And when you did that calculation, we got a big number. It was 2,000,000, let me see if I remember it, I don't think I have it on the top of my head, 2,598,960. Okay, that's always the number of 5-card hands of poker where order doesn't matter. So the answer could be written as the fraction 24 over that 2,598,960, right? But since it simplifies, we do expect you to do that. Calculators can simplify. If you don't know how to do that, you can come see me or email me, and I'll definitely help you learn how to simplify fractions by hand or on your calculator. But that does turn out to be, when you put that into your calculator or do it by hand, the fraction reduces nicely to 1 over 108,290. Now, if you put that in your calculator to get a better feel for the percentage or the likelihood of this happening, you would end up getting something where you see like E, and that's not error, but that's scientific notation. It'll say something probably like 9.23446E, and then it'll say negative, and it'll tell you like a number, -6 or something. And that would mean to move the decimal 6 places to the left. If it was positive, you'd move the decimal that many places to the right. It's just scientific notation because your calculator can't easily describe the numbers. It's too big or too small. Well, basically what that's saying is you have a very low likelihood of this happening. It's statistically close to 0%. So it's a very low likelihood. Okay, so if you're hoping and betting on this, I wouldn't count on it. Let's head to another example with combinations and probability. Example 2. It says find the probability of selecting a subgroup of 4 college-educated people from a party of 80 people, where 28 people in this party are known to have college degrees. Okay, just made up a problem. There's nothing important about whether they have a college degree or not. We're just trying to see what's the likelihood of this happening, right? So if you know a certain breakdown, whatever characteristic you're interested in, maybe these people have a certain type of car, or they like a certain type of food, we're just saying what's the likelihood that you select from this bigger group of people 4 people, and all 4 people are from this category. That's all we're saying. Okay, so let's think about what this would look like. Probability, okay, of doing what? Of selecting a 4-person subgroup from a party of 80 people. But in this subgroup, we want all 4 of them to be from this college-educated group, this characteristic. Okay, so let's take a look at what would need to happen. For the denominator, right, we think of how many ways could this happen, right? In the last problem, it was choosing 5 cards from 52. So 52 choose 5 was our denominator. This time, how many things or how many people are we choosing from the total? That's right, we're choosing 4 people, and the order doesn't matter because it didn't talk about any sort of prize or any difference in what happens to them, from the 80. So your denominator should be 80 combination 4. So that should be a pretty big number, right? That's the total number of ways that if you had 80 people in a room that you could make 4-person subgroups. Okay, so if you were dividing them into groups of 4, this will be the number of ways that can happen. Once again, feel free to use your calculator or the formula in order to get that number. I believe when I got that number in my calculator, it was a big number. It was 1,581,580. Okay, so that's the number of ways to choose 4 people from a group of 80 to be in a subgroup. Okay, so now what we're going to say is, what's the likelihood that when I picked my subgroup, it's going to be a specific type of person in my subgroup? What type of person? A college-educated one. Okay, well, how many college-educated people were in the party, or at the party? 28. Just like in the last problem, we wanted to know how many ways we could choose 3 kings and 2 5s. We had to first ask ourselves how many kings were in the deck, how many 5s were in the deck. There were 4, so we did 4 choose whatever number we were interested in. This time, there's 28 people in that category with that characteristic. And from that 28, we want to choose all 4 people, don't we? So 28 choose 4, 28 combination 4 would give us the number of ways that we can make that selection. Okay, again, use your calculator or use the formula. You should end up with 20,400 and 75. Okay. Now, technically, that is your entire numerator, but I wanted to show you a cool little trick here to keep yourself organized. If you're like me, you like to keep things very organized. So one thing that I like to do when I'm setting these problems up, these combination probability questions, is I like to make sure that I've accounted for everyone at the party or everyone in the deck of cards or whatever it is you're talking about. For example, I've talked about the 28 college-educated people, but by default, if you're only separating them by that one characteristic, then the other people at the party would not have a college degree, right? Maybe they started but didn't finish, something like that happened. So if we were to subtract 80 minus the 28 with the college degrees, I should say, how many would that leave us with? That's right, 52, right? So we'd have 52 people. Now from that category, are we choosing anyone? This time, no. But the reason I wanted to show you this is twofold. On the one hand, in some examples coming up, you're going to see, in your homework especially, where we want to take maybe 3 people from the college-educated group, but 1 person from the non-college-educated group. So it would be important to know how to set that up. 28 choose 3, 52 choose 1, right? Something like that would happen there. The second reason I wanted to show you that this is another way you could do the problem, to make it more orderly, is because now if I notice the 28 and the 52, they should be adding up, if I talked about everybody at the party, to 80. Right? And the 4 and the 0 should similarly be adding up to 4, right? So that's a nice way to keep yourself very organized and talk about all the people at the party so you know how many you took from each group. Okay, so if you're like me, you might find that interesting. It didn't have to be written though, because choosing 0 items, there's only one way to do that. You can use the formula or your calculator, you will get 0. How many ways can you choose nobody from a group of 52? One way, okay. So when you multiply this out, you'd get your numerator of just 20,475 and your denominator of 1,581,580. But this could be simplified again by dividing by 5 until you can no longer divide anymore. And you'll get 4,095 as your numerator and a denominator of 316,316. Now that's a nice exact answer for a math person, but for a real human, you might want to know what this means as a decimal. And so when I put it in my calculator, I got roughly 0.013 and change. So if I were to round that and make that a decimal, I would get roughly or approximately 1.3%. So that's pretty unlikely. You still have a better probability of this happening than getting that special hand of poker that we just did. But this is still very unlikely, and the reason is we were trying to see how likely it would be that at a party of 80 people, when we randomly choose 4 of them, that all 4 are going to have that characteristic which only 28 people had at a party of 80. So it was highly unlikely. If on the other hand I had said, what's the probability that 2 of them will be college educated and 2 of them won't be? This probability would rise because that's much more likely to happen. Okay, so let's have you try another problem just like this. I highly encourage you to pause it and try it yourself. It says find the probability in example 3 of selecting a committee of 2 students and 2 faculty members from a group of 8 students and 7 faculty members to represent the group when going to meet the campus president. Okay, so as soon as it says probability, you think fraction. Okay, so at this point, I'd encourage you to pause this video and see if you can set it up yourself. So here I had the probability of selecting a subgroup of students and faculty. And from the, let's see, the 8 students, I am selecting 2. So I want to choose 2 students from 8. And I also want to choose 2 faculty to be in this subgroup. And this is from 7. Okay. So we want to know how many ways could this happen, and then what's the probability of it happening, right? So for probability, we're thinking fraction. Now, what's the big picture that goes in the denominator? What are we doing in the big picture? Yes, that's right. We are taking a group of people and choosing a subgroup. Well, how many people were totally mentioned here? Yep, you had 8 students and you had 7 faculty. Altogether, that's a total of 8 plus 7 or 15. So from 15 humans, we are selecting how many to be on this subgroup? 2 plus 2. That's right, we're choosing 4 people altogether. So the number of ways that you could choose 4 people to be on a committee from a room of 15 individuals would be 15 combination 4, which again, use your technology, that's the faster way, or use the formula. You should end up getting 1,365 ways to do that. Now, of those 1,365 ways, how many are the way that we wanted it to happen, right? Where we have 2 students and 2 faculty. Nice even symmetry there. Well, the way we would have to do that is asking ourselves, from each category, how many were there and how many am I choosing, right? From the student category, there were 8 students, and I'm choosing how many? I would like to choose 2. Good job. So again, using your calculator or the formula, you do 8 choose 2 and eventually get 28 ways. Similarly, from the faculty category, we had a total of 7, right? So and means multiply. Multiply by 7, combination what? That's right, we're choosing 2. So use your calculator or the formula, you'll end up with 21. If you multiply that out or reduce first, either way is fine by me, you end up getting a numerator of 588 over this denominator. But when you reduce, you'll get 196 divided by 455. But what makes most sense to humans is the percentage, right? How likely is this to happen? We usually think percentages. It'll be roughly in your calculator 0.43 and change, so roughly 43%. So this is a much more likely situation. This is the most probable situation we've talked about all day in this video, right? So there's a almost a 50% chance, right? There's a pretty good chance that this could happen. It would still be more likely if you had added, let's say, another student. So if you did 3 students in one faculty, perhaps that might be more likely since there were technically more students than faculty just by 1, right? But since you did half and half, this was a pretty likely scenario since they were already pretty much evenly distributed. Okay. So let's head to another example. I believe this might, yeah, we're getting close to our last one. This will be our last example. So here we go. Try it on your own. Find the probability of selecting 2 cracked eggs when making brownies from a carton of a dozen eggs containing 3 cracked eggs. So if you're like me, you're in a hurry when you're shopping, and you might not check whether or not there are some cracked eggs in your carton. Here in America, we're very nice. They have nice cartons. Some countries I've lived in, they're just a bag of eggs and you have to kind of juggle. So yeah, we're still lucky to have a carton, but still you should check. So let's say you pick your carton at the store, you don't really check, you open it up to make your brownies, and the first egg you picked out, cracked. The second egg, cracked. The third egg, cracked. We're saying how likely was it that that happened? That's what the question is asking. Okay, so probability means fraction. You got it. So the probability that I select 2 cracked eggs from my carton. Okay, so that's going to need a fraction. What do we put in the denominator again? Hopefully you're just checking yourself. You tried it on your own, right? Yeah, for your denominator, you say, well, what was I doing? I was picking 2 eggs from the dozen. So from 12 eggs, I was selecting 2. How many ways can I select 2 eggs out of 12 if the order of eggs doesn't matter? That's a combination. Using technology or the formula, you should get 66 eventually. So there are 66 ways that you can choose 2 eggs from a carton of 12 where the order doesn't matter in which you select those 2 eggs. Okay, what about the numerator? Well, that's where we put the number of ways that what we would like to happen. I mean, in this case, we don't want to have cracked eggs, but we're saying how likely that is to happen. Well, from the cracked egg category, there were 3 of them, right? There were 3 cracked eggs. So we're saying that we're going to take those 3 cracked eggs and choose how many of them? Unfortunately, 2, okay? Now, technically, if you wanted to be consistent with what I mentioned earlier in the previous examples, you would also say, well, how many am I choosing from the other category, right? From the non-cracked category. Well, if there were 12 eggs and 3 of them are cracked, then there must be 9 which are not cracked. So we had a higher probability of choosing a non-cracked egg, which is nice. I didn't get a complete horrible carton, right? So 9 are not cracked. And how many of those are we saying are chosen in this problem? 0, right? So technically you didn't have to write that, but by writing it, you can keep track of everybody. The 3 plus the 9 gives me the 12, and the 2 plus the 0 gives me the 2. So that does line up nicely. In your calculator or with the formula, 3 choose 2 is just 3. So we're going to end up with 3 ways to select those 2 cracked eggs. And how many ways can you select none, I should say, from the non-defective eggs? 0. Sorry, I said 0. 1. Anything choose 0 is just 1. It's only one way to choose nothing, okay? And 3 times 1 is 3, so you just have 3 divided by 66, which does reduce nicely to 1 over 22. Now again, as a decimal, that's roughly 0.05 or roughly 5%. So the good news is, even though I didn't check my carton before I left the store, there's still only about a 5% chance that both of the eggs I pick when I go to make my brownies are cracked in this situation. All right, I hope this helped make sense of why combinations and when combinations are useful when order doesn't matter and you're selecting subgroups. At this point, it's up to you to practice making this your own because math is not a spectator sport. I'll see you next time.